Today's lecture will be on the high K and low K dielectrics as discussed earlier during our discussion on the dielectric film deposition, that in semiconductor processing we will have two types of materials. One is the low K, K means the dielectric constant, another is the high K or the high dielectric constant. Both type of materials we have to process for finishing a IC chip or a discrete device. Now, if we see at the view graphs, why this low K is required? As discussed earlier, this low K is required to minimize the time delay in an interconnection architecture. So, now if you consider this interconnection architecture, you can find that a large number of metal lines are there which were connected, say in this case the copper connected with the tungsten to another copper. So, there will be a interconnection of the metals, and that is required for the finishing of the device, that means for the connections of the one device to the other, one function with the other, and this is for the interconnection inside in the device itself. Now, to minimize the time delay. Now, what is the time delay? Time delay is basically the product of R and C, where R is the resistance and C is the capacitance. So, you can see that this time delay, which is a product of R and C, that must be minimized. Now, how to minimize R and how to minimize C? Now, if you see that this R can be minimized by using, say in case of copper, if you compare with the aluminum, R for copper is less. So, the metal interconnect which we shall use, that will minimize the R, and that C, the value of C will be minimized by the low dielectric constant. Why? Because if you see that C, the capacitance is given by the dielectric constant of the material multiplied by the free space permittivity divided by the thickness and multiplied by the area. So, now if you want to minimize C, you have to minimize A, but minimize A is very difficult, because in that case you will see that if you reduce A, the interconnect resistance will increase. So, we do not want, because the interconnect resistance in this case will be increased. Epsilon 0, that means the free space permittivity, it has a constant value 8.85 into 10 to the power minus 12 farad per meter, and D is the thickness. One approach can be that you can minimize the you can maximize D, you can increase D, but if you increase D, then there will be a problem with the gap filling. The gap filling will be difficult, because if you increase the thickness, then those gaps you have to fill with some materials, and which will be very difficult. So, we have no other option but to reduce the value of K. So, that is the logic, that for an interconnection architecture, if you want to make time delay as minimum as possible, you have no other option but to decrease both R and C. But so far as the R is constant, you can use any low resistive material, say copper is widely used, aluminum can be used, but copper is better than aluminum, or even you can use silver and gold for discrete device in some cases, so that the resistance will be further minimum, and the capacitance can be minimized by the minimum value of K, which is the low dielectric constant material. Now, in that case, if you minimize, it is okay, otherwise what will happen? The interconnection network becomes a limiting factor in determining chip performance. What are the chip performance? Such as the power consumption will be high, device speed will be low, there will be crosstalk in ultra large scale integration. So, it justifies the use of low K material in interconnection network, which is a basic processing in the ULSI or the ultra large scale integration chips. This figure, which we have shown earlier also in case of our discussion on the dielectric film deposition, that if you reduce the feature length, that means if you go on decreasing the length of the feature size, that means for nano devices say or scaling down, then what happens? The gate delay will be reduced, but at the same time the interconnection delay will be increased, because you see that the interconnection delay is delay increases with the minimum feature length. Here in the X scale you see that we have started from 650 to 100. So, that means it is decreasing. So, as the minimum feature length decreasing, the gate delay increases, and it increases by such a factor that even if you take the sum of the delays, so it will be dominated by the gate delay. So, that is why here we have written that limiting factor will be the device interconnection network. So, device interconnection must have the minimum value of the time delay or RC. Now, what would be the criteria? This is the criteria that low K dielectric must have these properties, and you see that when we talk about low K dielectric, it means the value of the dielectric constant will be less than 3. It must be isotropic. So far as the isotropic is concerned, it must be the value will not have any direction dependence. In all the directions you will find that the value will be same, whether you take in the x direction or the y direction. So, in all the directions the value of the dielectric constant will be same. Also the dielectric must be able to have high breakdown voltage, because otherwise there will be breakdown, there will be large tunneling. So, the leakage current will increase. So, the property must be the value you have to choose or the material you have to choose in such a manner that the material must be must support very low leakage current, or it will have very high breakdown voltage and the high reliability. Another properties are the mechanical good adhesion to metal or other dielectrics it must have. It must be low brittleness, crack resistance, uniform thickness processing is possible. Then it must have low thermal expansion or shrinkage, high thermal stability, high thermal conductivity. Then chemical properties, that there will not be any metal corrosion, and it will have low solubility in water, low defect density and environment friendly. Now, a lot of materials, these materials we have shown earlier also, that a lot of materials are there which we can make by either the vapor phase deposition, or that means the CVD, or spin on deposition SOD. These are almost all of them are polymers except a few, and here you see that the dielectric constants are almost 3 or less. Now, one material can be say MSQ, and this is inorganic organic hybrid material. The chemical structure is shown, and the brand name of this material which is available in the market is HOSP HOSP. It is from the Honeywell, and it has the dielectric constant low 2. This is an hybrid organosiloxane polymer, and hybrid organosiloxane polymer, it has 70% MSQ, that means methyl silsesquinoxane, and 30% HSQ, that means hydrogen silsesquinoxane. And this material is basically a carbon doped oxide. It has very high thermal stability, it has very high resistance to cracks and reactant with stripping chemicals. So, these are the main feature of this material which is available in industry. Then another material can be PAE, polyarylene ether. You can see that here we have PAE or polyarylene ethers. So, depending on its chemical structure, it can have value 2.6 or even less. In this particular case, which is known as the flare, available from the Honeywell or Sumasar, the Velox. These two material brand name, those are the proprietary item of Honeywell and Sumasar, and it has the dielectric constant 2. The chemical diagram is shown, and it has very high thermal stability, low moisture absorption, good adhesion with metals and SiO2, and anisotropic, that we have discussed earlier, that this anisotropic is basically the value is not a fixed one, it can have different values at different directions. So, this is one of the problem, but it can be solved if we can go on increasing the K by say 2.6 or 2.8, then it will be isotropic and not anisotropic. The next material can be parylene N with K equals to 2.7 or parylene F K equals to 2.4, and parylene N has mechanical stability, mechanically it is very stable, high thermal stability, poor adhesion with copper, and parylene F has the same properties as parylene N, and poor adhesion can lead to corrosion. So, that is one of the disadvantage of parylene. And then it can be another material can be organic material, which is known as B stage polymer, having value K equal to 2.6. B stage means benzocyclobutane based polymers, and there are two materials available from in the market, and both are from the Dow Chemical, they are the proprietary items. One is cyclotine, another is silk, SILK. Cyclotine is a fluorine based material, it has good temperature stability, low metal adhesion, moisture absorption, and currently used in gallium arsenide interlayer dielectric. So, that is very important thing. We shall discuss about this gallium arsenide, because as discussed several times during our last 38-39 lectures, that gallium arsenide or 3,5 semiconductor has certain advantages over silicon dioxide system, so far as the MOS devices are concerned. And today we shall discuss some of the features of gallium arsenide based MOS, where we shall use the high K dielectrics. So, and in this case you see that the interlayer dielectric currently used with gallium arsenide is basically the cyclotine available from the Dow Chemical. Or the other material, say silk, SILK, it is a phosphorus based material, it has also high temperature stability, good metal adhesion and low mechanical stability. So, if we go back to this properties, we have that the mechanical property will have to be good adhesion to metal, that is very important, and it will have high thermal stability also. So, in this case we see that it has low mechanical stability, and cyclotine has low metal adhesion. So, some limitations are also there so far as those materials are concerned. Another material is PTFE, it is water based polytetrafluoroethylene PTFE, that means Teflon etc. That is a siloxane nano composite. The chemical structure is shown, and from WL Gore and Associates one material is available having the polytetrafluoroethylene, that is derivative of this thing, is the speed film. It has no moisture absorption, it has the property of temperature resistance, it has good adhesion with metals, it has good mechanical stability and compatible with etching chemistries. That is also important, because in some of the cases we will find that etching must be done. So, this Teflon or the PTFE is one such materials having K is very low 1.9, having these properties, and it is also industrially available in the name of speed film from WL Gore and Associates. So, now with this discussion we can conclude, so far as the low K materials are concerned, it is very important that this material is used in the interconnection, and this interconnection must have, this interconnection network must have the low RC value, and with this low RC value we do not have to, we do not change R, generally the copper is used having very low R, but C we can have different types of materials as discussed earlier. Then with that material it around 2 value of the dielectric constant is the best one, and different materials we have considered having some limitations as well also, and industrially available. Some of the materials are used in the present day semiconductor process lines. And now we shall take one example, numerical example, using which we can and substantiate our view that the value of C must be less in case of the low dielectric materials, which is the requirement. One such example is that estimate the intrinsic RC value of two parallel aluminum wires 0.5 micrometer by 0.5 micrometer in cross section. So, this is basically a square cross section, and 1 millimeter in length and separated by a polyimide value K, that is dielectric constant as 2.7 film, that is 0.5 micron thick, given resistivity of aluminum is 2.5 micro ohm centimeter. So, let me repeat, estimate the intrinsic RC value of two parallel aluminum wires 0.5 micron by 0.5 micron in cross section, 1 millimeter in length and separated by a polyimide film that is 0.5 micron thick and the dielectric constant 2.7, given resistivity of aluminum 2.7 micro ohm centimeter. Now, if we want to solve this problem, RC, R into C, R is equal to rho into we know L by A area, and area is equals to here the cross section 0.5 by 0.5 micron. So, let us say that this is T m, the dimension, and C is given by epsilon r multiplied by T m into L, because area by the spacing SPACING width D. That means, it is epsilon I is nothing but the epsilon 0, epsilon I in this case it is epsilon 0 multiplied by the k is given. Okay. So, now with this relation let us solve this problem, and what is the value of rho? Rho is given by 2.7 micro ohm centimeter. So, it is 2.7 into 10 to the power minus 6, then it becomes ohm centimeter, multiplied by L. L is 1 millimeter, L is 1 millimeter you can find. So, it will be 1 into 10 to the power minus 1 centimeter by T m square is 0.5 micron by 0.5 micron, that means 0.25 micron and square, and it will be multiplied by 10 to the power minus 8 to arrive at the centimeter. So, that is the value of R and in CGS unit, and then epsilon r I is k into epsilon 0. What is k? K is 2.7, it is given K is 2.7, then multiplied by 8.85 into 10 to the power minus 14 in CGS unit, farad per centimeter. Then Tm is 0.5 micron into 10 to the power minus 4 in centimeter into L 1 millimeter 1 into 10 to the power minus 1 centimeter, and spacing D is again 0.5 micron, 0.5 micron thick. So, D is 0.5 micron and it is 0.5 into 10 to the power minus 4 centimeter. So, with this we find that the value of RC, that means that delay is 258 if you multiply and work out with some manipulation 258 into 10 to the power minus 14 second. That means 2.58 into 10 to the power minus 12 second, and which is equals to 2.58 picosecond. So, we find that this is very small, 2.58 picosecond, and here we must say that the value of RC is basically the in the time is the dimension, because R is equals to, you can consider V by I and this I is Q by T. So, V into by Q into T, and then this is farad and that is also a farad, C is in farad, it is 1 by farad. So, that will be the second or the time. So, now if you go towards the lower resistive material, say from aluminum to copper or from copper to silver or silver to gold, etc., you can find that this is 2.7 will further go down and this is in the numerator. So, as this value will decrease, RC time constant will further decrease. So, that is an estimation of the time delay in a RC network where aluminum and polyimide is used, or if you can use that instead of polyimide some other film. So, this will go down and that resistivity will also go down at the same time if you use the copper or silver. So, further reduction of the time delay is possible. Now, we talk about the high K dielectric. This high K dielectric is a very important material for dynamic random access memory. This dynamic random access memory is useful in case of the memory devices, and the storage capacitance, you can see that in DRAM the storage capacitor has to maintain a minimum value, has to maintain a certain value of the capacitance, Here again we make use of this relation, that means the capacitance C equals to K epsilon 0 by D into A, where K is the dielectric constant, epsilon 0 is the free space permittivity, D is the thickness and A is the area. Now, you can if you want to increase C, suppose we want to increase C because the storage capacitor must have some maintain some certain value. So, now what is the requirement? Requirement is that D can be less to increase C, D can be less, but if you can make D very small, then there will be leakage current problem. So, D is limited by the leakage current, the thickness is limited by the leakage current. You cannot take any value of D. If you want to take D very small value, then there will be leakage current, there can be breakdown problem, and so it is limited by the maximum allowed leakage current. So, it is limited by the maximum allowed leakage current and minimum required breakdown voltage. Now, for planar structure, A is reduced to increase DRAM density by making stack and strange, etc. So, that is possible, Otherwise, if you can make A very large, then there will be the problem of the scaling down. You cannot go to very small structure. So, we have no other option but to increase the value of K. So, that is why the high K dielectric is the solution. Now, a large number of materials we find that are available in the market or one can synthesis. These are the SiO2 having dielectric constant 3.9, then Si3 and 4 we have discussed the SiO2 and Si3 and 4 earlier, the dielectric constant is 6.3. Then a large number of materials like Al2O3, hafnium oxide, tantalum oxide, zirconium oxide, titanium oxide, strontium titanate, PZT, that means lead zirconium titanate, a large number of materials having dielectric constant you see 3.9 is the lowest for SiO2 which we regularly use for SiO2 device to 300, very large value, and band gap also you can see the tabulation has been done. Then conduction band offset has also been shown with minimum with the breakdown voltage in megavolt per centimeter. For SiO2 it is the highest and for PZT is the lowest. So, almost an inverse relation is obtained so far as the dielectric constant and breakdown is concerned. So, we see that if we plot this value, the breakdown field it is in megavolt per centimeter in the y axis and dielectric constant in the x axis, we can see that as the dielectric constant increases, the breakdown field decreases. So, we cannot take any value of the dielectric constant, because in that case we shall have the breakdown field, we have to face or we have to encounter the low breakdown field, and so there will be breakdown and the device cannot have any stability or reliability. So, that is one of the major thing, that even that the SiO2 has the lowest dielectric constant of 3.9, it is widely used till now. However, if you find some of the material some of the dielectric metal oxides like say TiO2, ZrO2, hafnium oxide, tantalum oxide, those are used because the dielectric field which have they have for a particular dielectric constant is allowed in some of the cases. So, people can use TiO2, ZrO2, hafnium oxide, tantalum oxide, etc., because the dielectric constant is very high. If you consider HFO2 it is 21, zirconium 25, titanium 30. So, very high value, almost 8 times 7 times higher than SiO2, and the breakdown field you see that the breakdown field of SiO2 is say around 10 point something, whereas for zirconium or hafnium for zirconium etc., it is say 1, 2, 3, 4, almost 4, 5, 2 etc. So, those are basically the values which one can make use of, and so there is no harm if we can replace SiO2 in some of the systems with the newer metal oxides. Now, problem with the silicon dioxide is that it has some limitations, like electron direct tunnel probability is high. As you go on reducing the physical thickness of the SiO2 layer, then there will be some electron tunneling probability as you scale down the silicon device. So, the thickness of the silicon dioxide will have to be reduced, but in that case you see that this capacitance per unit area, it is given by this relation, and the equivalent oxide thickness or the oxide, it is basically K by T ox. So, now the thickness if you can make very small, COX will be high, but with the TOX will, if TOX is small, then there will be direct tunnel probability, high leakage current will be there, the power dissipation will also increase, and so equivalent oxide thickness will be the limiting factor. And also we can see that the saturation drain current is basically the function of the mu, the mobility multiplied by the oxide capacitance COX. So, if we want ID sat to be increased, then COX must be increased for a particular value, because mu is fixed in that case. So, with greater physical thickness and high K values, the leakage current is reduced and oxide capacitance is increased. So, that is very important thing, and for scaling down you cannot go with greater physical thickness. So, these are the limitations of SiO2. Now, if we consider that the replacement, then there will be some high K dielectric, and that is an essential requirement for fabrication of MOS capacitor. Now, this gallium arsenide, what are the benefits of gallium arsenide as channel materials? It has high electron mobility. The electron mobility of silicon is 1800 centimeter square per volt second, but in case of gallium arsenide it is almost 9000 or above 9000. So, 5 times higher compared to silicon. Then it has high breakdown field, low power consumption, for high speed and high power application it is used, and it features a large drain current, much lower gate leakage current, a better noise margin, and much greater flexibility in digital integrated circuit design. So, these are the advantages of gallium arsenide over silicon. So, gallium arsenide can be a good choice for future generation MOS devices or say for memory devices, but it has some limitations also. Found no stable oxide like SiO2 on silicon, because you see that SiO2 is the oxide, it is basically the oxide of silicon, but it is the native oxide. However, in case of gallium arsenide, the native oxides are gallium oxide or arsenic oxide, because that is a binary compound. Gallium will have its own oxides, arsenic will have its own oxides, and these are poor native oxides, very poor properties. Electrical properties are very poor, and Fermi level pinning at the interface between high K and semiconductor is also there, Fermi level pinning, and high threshold voltage back getting and side getting effect, and high interface trap density. So, these are the limitations of gallium arsenide based MOS devices. If you want to make some MOS devices to replace silicon with gallium oxide or arsenic oxide, then these are the problems. And so, what one can do, that you can make some interface passivation layer between gallium arsenide and high K. Suppose this is your gallium arsenide, and with this is your gallium arsenide, and with this gallium arsenide, before making a layer of say high K dielectrics, you passivate the gallium arsenide surface itself. So, you can make use of the interface passivation layer, and different chemical treatments you can use, like people have made some sulfur treatment, ammonium sulphide they have used, chemically treated the surface to reduce the native oxides etc., that means to clean the surface, to deepen the Fermi level, because from the gallium oxide or arsenic oxide bonds there will be pinning of the Fermi level, and also because of those oxides, poor native oxides, the interface trap density is also very high in case of gallium arsenide based device. So, one can make use of the interface passivation layer, and different types of interface passivation layer people have used. SiO2 has been used, Al2O3 has been used, zinc oxide is used, indium phosphide pseudomorphic layer is used. So, that is the solution, that interface passivation layer is made, and it is essential between gallium arsenide and high K. Now, if we consider different interface passivation layer, say sulfur layer, germanium layer, silicon layer, aluminum oxynitride layer, titanium nitride layer, Si2 is we have shown as a benchmark, because we shall compare the values of the different interface passivation layer with the SiO2 MOS. Now, if we use a sulfur interface passivation layer, that means sulfur passivation on gallium arsenide before the deposition of high K, then we can see that the some of the properties, these are the properties that we can compare. What is the DIT value? DIT is the interface trap density. The value has been shown in centimeter square inverse electron volt inverse. So, with sulfur passivation, the gallium arsenide based MOS capacitor will have DIT value 5 into 10 to the power 11. With a germanium treatment, germanium layer 5 into 10 to the power 11. With silicon, no such values is available. Aluminum oxynitride 6.9 into 10 to the power 12, and for titanium nitride no such values available. Now, what we find that this treatment is made on the gallium arsenide surface. However, the dielectrics or the oxides which are used over that gallium arsenide surface is different. In this sulfur treatment, we have used aluminum oxide Al2O3. The thickness of Al2O3 is 10.5, and with this value of a dielectric layer over gallium arsenide with sulfur treatment, the leakage current is found to be very small, 3 into 10 to the power minus 8 ampere per centimeter square at minus 1 volt. Then DIT is also reasonable and hysteresis is 0.43 volt. Then germanium with hafnium oxide as dielectric and germanium 1.5 nanometer thickness. The value of the leakage current is not very good, 3 into 10 to the power minus 4. So, it has basically, so far as the leakage current is concerned, there is a increase in the leakage current at the same voltage of minus 1 volt. However, the DIT is same 5 into 10 to the power 11 and hysteresis has improved 0.27 from 0.43. Then if we use a silicon layer, this silicon passivation means take a gallium arsenide wafer on which you deposit 1.5 nanometer silicon and then 7 nanometer hafnium oxide. With that structure, the leakage current is 10 to the power minus 6 ampere per centimeter square and hysteresis is 0.8. So, this is not a solution because we see that both the hysteresis and the leakage current has increased so far as the sulfur treatment is concerned. Then with aluminum oxynitride it is 2.8 into 10 to the power minus 5, not bad, but even with sulfur it is very less compared to aluminum oxynitride, and DIT value, the interface trap density is 6.9 into 10 to the power 12, which is very high, and with titanium nitride with the value is 10 to the power minus 6 leakage current, and if we compare with SiSiO2 system, that means SiSiO2 as a benchmark. So, DIT we have to go to 10 to the power 10, and till now such small value or such lower value of DIT is not possible, and leakage current we have found that lowest is in case of the sulfur treatment, which is 3 into 10 to the power minus 8. Even SiSiO2 has the large leakage 10 to the power minus 5, which is comparable, which is even worse compared to other surface treatment or surface passivated gallium arsenide MOS devices. Now, the technology which one can use at this moment for the gallium arsenide surface passivation or treatment is the sulfur, because the leakage current is very less compared to SiSiO2 as benchmark, and DIT value is obviously greater than SiSiO2, but it is 5 into 10 to the power 11, a reasonable value. Now, with this thing, if you sulfur treat the surface, suppose if you take a gallium arsenide wafer on which you make some sulfur treatment, then you deposit the oxides, after treatment you deposit the oxides. So, that means effectively the cross sectional view will be this is the gallium arsenide on which there will be a sulfur treatment, the red region is the sulfur treatment, and on which you can make use of different type of oxides. So, this is the black one is the oxides. See, with this treatment what we find that this is the photoluminescence of sulfur passivated and unpassivated gallium arsenide. With sulfur passivation we see that the intensity increased, and without sulfur passivation, if we compare these two, the intensity increased with sulfur passivation, and the treatment was done with the ammonium sulphide chemical solution. Why this is not a perfectly Gaussian curve? Because this is taken at room temperature. So, there will be different kinds of broadening etc. And another confirmation that one can make with the XPS, X-ray photoelectron spectroscopy. This is the XPS spectrum for S2P. In the x axis binding energy has been shown, and this is the characteristics binding energy for S2P. This is the confirmation of sulfur. And with their thing on sulfur, we have used the titanium oxide as the dielectric layer. That means, this black layer which we have shown is TiO2, titanium dioxide. Then with titanium dioxide we have used the Raman spectroscopy as well as the XPS to confirm the formation of TiO2 on the gallium arsenide substrate. This is the frequency dispersion. This is the CV characteristics of the sulfur treated devices, where we can see that we have used titanium oxide and aluminum as the gate electrode. The frequency dispersion is very small, almost 4.9% per decade, because here we have used 3 frequencies. The blue one is 10 kilohertz, the red one is 100 kilohertz, and the black one is 1 megahertz. So, at lower voltages you can see that -2, -3 voltage, that is obviously a dispersion, but the dispersion is very low, 4.9% per decade. Now, this is the cross sectional high resolution TEM of gallium arsenide TiO2 structure, where between gallium arsenide TiO2 we have made use of sulfur. This is the sulfur transition region, gallium arsenide and TiO2. So, a smooth interface is obtained, and this is the CV characteristics, that means the earlier one, that is at different frequencies, but here we have used different thickness of TiO2. 3 types of thickness we have, 3 thicknesses we have used. One is 33 nanometer, the black one, and red one is 54 nanometer, and the blue one is 71 nanometer. The measurements were taken at a frequency of 1 megahertz, and it is the conductance frequency plot for 3 different thickness of the TiO2. Now, from these measurements we have calculated the DIT value. DIT value we have calculated, and we see that oxide thickness value, if you increase 33 to 54 to 71, the equivalent oxide thickness also increases. The dielectric constant is almost same from 26.7 to 27, and DIT value we can find that it is increased 1.4 into 10 to the power 11 to 1.84 into 10 to the power 11 to 2.9 into 10 to the power 11. Now, the values we have measured, the DIT value we have measured from the conductance technique, that means from this plot with this equation, and we see that in one case if you use the series resistance, RS is the series resistance, and this series resistance you can include or you cannot. If you include series resistance, the value will be high, 4.2 into 10 to the power 11. However, without series resistance 3.4 into 10 to the power 11. So, non inclusion of series resistance may change the DIT value. So, that is very important thing that one must consider. And this is the this plot we have shown earlier also. Here the tangent loss versus voltage plot, and in the inset it is the conductivity versus voltage plot. For different type of thickness we have measured the conductance versus voltage. A MOS device with high K dielectric has small leakage current compared to its displacement current. Loss tangent is defined, this is a loss tangent, it is defined as the ratio of the leakage current, to the displacement current. And when the voltage is increased beyond -1 volt, the leakage current gets saturated. However, the displacement current increases, so the dielectric loss tangent will decrease. So, displacement current increases, that is why the dielectric loss tangent decreases. It was also observed that the loss tangent peak increase will increase in oxide thickness, and at a voltage of -1 volt, the current density was found to be the order of 10 to the power -7, 10 to the power -6 and 10 to the power -5 ampere per centimeter square for TiO2 thickness of 71, 54 and 33. The red one is 33 and the blue one is 54 and black one is 71. So, this is the IV characteristics, that means current density versus voltage. At a particular voltage, say -1 volt, we have compared, and with a TiO2 thickness of 71, it is very high, 10 to the power -7 ampere per centimeter square is very good value, because with sulfur treatment and with say, and here with sulfur treatment and Al2O3, we have seen that it is 3 into 10 to the power 8, and here we have not used the Al2O3, rather we have used the TiO2 and it is 10 to the power -7. The current increased with the decrease in the thickness of TiO2 layer because of the increase in the transmission probability. Now, here the current density is plotted as a function of voltage at different temperatures from 100 K to 290 K in the 4 values. At -1 V, the leakage current is found to decrease by 2 orders of magnitude, while the temperature goes down for 290 K to 100 K, 2 orders of magnitude. This reduction in leakage current density at low temperature suggests that thermally excited carriers play a vital role in the current conduction at room temperature. And here with zirconium, then the sulfur passivation has been done. Earlier works were related to TiO2 and this is related to zirconium. We can find that the XPS spectra has been shown to prove the formation of ZrO2, Zr3d 5/2, Zr3d 3/2, 2 peaks are obtained, and in the inset oxygen 1s core level spectrum has been shown. In this case, it is the HRTM image that between gallium arsenide and zirconium a sulfur passivation layer is obtained, and then XPS spectra has been taken with and without sulfur passivation. In one it is with sulfur passivation, in 2 without sulfur passivation. So, what we find that this is the arsenic 3D spectrum and this is the arsenic oxide, and this arsenic oxide has been decreased. This is very sharp peak, here it is mirrored out. So, with sulfur passivation we find that there is a considerable decrease in arsenic oxygen bond. Here also the gallium oxide is very high. Here the gallium oxide, you see that this is without sulfur passivation and compared to this it is very high. So, the sulfur passivation has reduced both gallium oxygen and arsenic oxygen bonds on the gallium arsenide surface. So, the poor electrical performance due to these native oxides of gallium arsenide could be eliminated, which can be enhanced, the characteristics can be enhanced, and at the same time we find that this is the origin of the Fermi level pinning. So, there is a possibility that de-pinning has been obtained. Now, what are the effect of sulfur passivation on electrical characteristics? The effect of sulfur passivation on electrical characteristics is that here the upper curve is the sulfur passivated structure and the lower the bottom one is the structure without any sulfur passivation. And in the inset we have shown the current density versus voltage. Here also we can find that the very low leakage current with sulfur 10 to the power minus 7 ampere per centimeter square at minus 1 volt, and hysteresis voltage is 150 millivolt for passivated, and without passivated it is 400 millivolt. So, we see that the very low leakage current is obtained with sulfur passivation, and the hysteresis also has gone down from 400 millivolt to 150 millivolt. The frequency dispersion is, we have seen that it is 2% per decade. Then the values of DIT, which is measured by the conductance techniques, it is obtained as 0.75 into 10 to the power 12 to 2.4 into 10 to the power 12, not very encouraging. And as the dielectric layer thickness increases, more and more strain is developed in the interface, leading to higher interface trap density. And this value of DIT are found to be 1.5 into 10 to the power 12, 2.2 into 10 to the power 12 and 3.8 into 10 to the power 12 for the substrate doping concentration of 1 into 10 to the power 14, 2.5 into 10 to the power 15 and 3 into 10 to the power 16. So, basically this is the capacitance voltage characteristics with different thickness of ZrO2. This is the CV characteristics with surface substrate concentration different 10 to the power 14 to 10 to the power 16. It is found that with increased doping concentration, DIT increases possibly due to the exposed ions. Now, dielectric loss K double prime versus voltage for aluminum, zirconium, gallium arsenide MOS devices, and this is the dielectric loss tan delta, and this is the AC conductivity. So, both all the properties, that means the dielectric loss, the loss tangent and AC conductivity, we can find that these values decrease with increasing frequency due to the presence of interface polarization mechanism, and these interface states cannot follow the AC signal at high frequencies. And the value of AC conductance decreases with the decreasing frequency, possibly due to the effect of series resistance. So, we find that this is very important technology, that if you use the gallium arsenide based MOS devices, then better you make a sulfur treatment, and if you do not have some facilities like the atomic layer deposition or MOCVD deposition of very thin pseudomorphic layers of 3,5 or 2,6 semiconductors over gallium arsenide, which also have been found to pacify the passivate the surfaces to reduce the interface trap density and to deepening the Fermi level. Now, here you see that at different temperatures the current density is plotted as a function of voltage, and since the current transport across the interface is a temperature activated process, electrons at low temperatures are able to surmount the lower barriers, and so transport mechanism will be dominated by the current flowing through the lower barrier height, and consequently ideality factor will be larger. As the temperature increases, more and more electrons gain sufficient energy to surmount the higher barrier, and as a result the apparent barrier height will increase with the temperature. So, we see that the barrier height increases with temperature. At the same time the ideality factor decreases, and increases an apparent increase in the ideality factor and decrease in the barrier height at low temperatures are caused possibly by effects such as non-uniformity of the interfacial charges, barrier inhomogeneities at the interface and potential drop across oxide layers. So, these are the things that one can evaluate. So, what are the parameters that one can evaluate from the MOS devices. One is the leakage current, which must be very small. Second one will be the hysteresis, which also will be very small, because in that case we can conclude that if the hysteresis is very low, then the trapping charges are low. So, DIT value will be obviously low, and the value of the hysteresis will be low. At the same time, the interface trap density. So, that means one factor is the interface trap density, number 2 is the hysteresis, and number 3 is the leakage current. These are the 3 important parameters that one can evaluate for a particular MOS devices. And in this view graph, as discussed earlier, that we have the benchmark as SiO2. So, these 3 parameters, that means the hysteresis, DIT and leakage current, one must be comparable with the SiO2 system to obtain the low values of these parameters for application in the gallium arsenide based MOS devices. So, if we conclude today's discussion, what we find that one thing is the application of the low K dielectric material in the RC network interconnection network system. We must have RC value low, as low as possible, and this low value of the delay, which is the product of RC, is coming from the value of the C. So, the value of C must be very low, and C is a function of both area and inversely proportional to the thickness of the material, but thickness you cannot make very small because of the breakdown as well as the leakage current, and also because of the scaling of the MOS devices, one or the ultra large scale integration, you cannot go beyond a certain value of the area, and at the same time if the area is becoming large, then obviously there will be if the area is becoming small, then there will be the increase in the resistance of the interconnection network. At the same time, for the high K material, we have seen that that is very important in case of the MOS devices, in case of the DRAM devices, and for scaling down we cannot make A very large or D very small, because making D very small we will have the possibility of breakdown at the same time of very high leakage current. So, we have no other option but to increase the value of C, and both the high K and low K materials we have seen that they have their own advantages in different systems. We have discussed many materials in this connection, and one important thing we have seen that for low K it must be less than 3, and it can be an organic material, it can be an organic inorganic hybrid material. There are many materials available in the industry, particularly which are being regularly used in the existing semiconductor process lines. And for high K material, one important aspect is that if we increase the dielectric constant of a particular material, then the breakdown field will be decreased, and so if the breakdown field decreases, the your devices will have no stability, no reliability, and there will be breakdown of the device. So, one must play around that what should be the value of the breakdown voltage, and with that voltage what are the possibilities that one can use of a material, one can use what type of material with the value of the breakdown voltage, and there are many choices like we have seen apart from SiO2, then hafnium oxide, titanium oxide, zirconium oxide, tantalum oxide, many oxide metal oxides are also available, and those one can make use. And so, at the end of this lecture we can say that for ultra large scale integration, apart from SiO2, silicon nitride is important. SiO2 has been seen to use as a field oxide, as a gate oxide, silicon nitride for passivation, for anti scratching, for resistor barriers for moisture and different type of impurities. Then we have make use of polysilicon, and finally, the high K and low K materials for different applications. Thank you.